seen, sort of seen, not really explicitly seen, but think about it. Addition and subtraction of vectors in 3D is completely identical to addition and subtraction of vectors in 2D. In other words, everybody look at your model. Put your finger, or imagine putting your finger at the tail of U. Travel the vector U1 plus U2. So if you travel U1 plus U2, it should take you over to the head of U, right? So what's a shorter way to get from the tail of U to the head of U? Instead of going along U1 and U2, just travel along vector what? U, correct. So in other words, U1 plus U2 is U, correct. That's the same thing we had on a two-dimensional plane. Now it's just a 3D field. Okay, so addition subtraction actually is identical in 2 dimensions and 3 dimensions. And we've also discussed a type of product. We actually designed a product where if you multiply vector by vector, you get a number. And we very carefully designed it where if you multiply a vector by itself, it will give you the same thing as multiplying the vector's magnitude by itself. So we tried to multiply 3, 4, and 3, 4 so that we would get 5 times 5. So we actually said you have to multiply the x's first, then multiply the y's next, and then add. Okay, so that's how dot multiplication emerged. It was sort of a desire of ours to invent that. So go and fill in the blanks here. This is dot multiplication. Now I'd like you to find the dot product for these two vectors, just to make sure everybody's doing it right. Because actually, even in the two-dimensional case on the quiz, some of you did the dot product wrong on the two-dimensional case. So we're going to be toast when we hit 3D. Okay, I'm going to pause it, and you guys work this dot product. Okay, did you guys get negative 15? Okay, so it's 2 times 4, 8. Negative 1 times 5, negative 5. And the 3 times negative 6, negative 15. Okay, let's see here. Now, dot products are pretty easy, right? But what if we wanted to create another type of multiplication that doesn't give us a number answer but gives us a vector answer? So we seek a product of two vectors that itself is a vector. Okay, this type of multiplication is not defined well in 2 dimensions. That's why I waited to teach it today, because we needed our 3D vectors in front of our face to really understand this properly. Okay, that's why everything was built, and now we can talk about this second type of multiplication, and it's going to be a lot more meaningful. Okay, so it says, unfortunately, this type of multiplication is not well defined in 2D. Consequently, we'll be spending most of the rest of this unit working with 3D vectors. To do vector products, or cross products, or exterior products, we call them. There's 3 names for them. We need to review matrix determinants. So this is something that you learned in Algebra 2 honors, and let's see if you remember it. If you don't, sit tight for 3 minutes. But see if you can find the determinant of this 3 by 3 matrix. Okay, so it's really hard to remember stuff like this. Okay, and it's partly because of the way that high schoolers learn determinants. They're a lot harder to understand when you learn a lot of tricks. There's nothing wrong with doing tricks to do your determinant quickly, but there is a formal way to do all determinants, whether it's a 2 by 2 or 3 by 3 or 5 by 5 or 20 by 20. Okay? But the fastest way is to use the trick you learned last year, so that's the trick I'm going to use. I will teach you another way to do it when we get to chapter 10, and you'll find that that method works on a 4 by 4 or a 10 by 10. What I'm about to show you only works on a 3 by 3. So first you take the first column and the second column, and you just copy them outside the box. So right on top of the equal sign, write 2, 3, 5, and 7, 4, 0. How many of you remembered that step? Okay, so like I said, not everybody's even seen this before. Okay, so then what we do is we draw diagonal lines that go down and to the right. So these green lines, 2, 4, 9, 7, 1, 5, negative 2, 3, 0. So you draw diagonal lines going down. You then multiply along those lines. So what is 2 times 4 times 9? And what is 7 times 1 times 5? And what is negative 2 times 3 times 0? Okay, you take these 3 green numbers and you add them together. This gives us 107. So it's almost like doing a dot product, but instead of doing first and last, it's more like diagonal elements. Okay. Then we do the same thing going up the page. So I'll draw that with a blue pen. 5 times 4 times negative 2, 0 times 1 times 2, 9 times 3 times 7. So let's write down those three products as well. So what's 5 times 4 times negative 2? Negative 40, yeah, because it's 20 times negative 2. Good. What's 0 times 1 times 2? 0. And what's 9 times 3 times 7? It's 27 times 7, or 9 times 81 is probably the easier. 9 times 21, that's probably the easier way to think of it. 9 times 21, so 189. Okay. And then we add those three blue numbers. 149. Okay, here's the trick. The part that people mess up on the most. All along we've been multiplying and adding, all along. And now we're going to do one final subtraction. Green minus blue. So 107 minus 149. Our final answer is, in this case, and it's not always this way, but in this problem it's a negative answer. We got 42. Negative 42. This number has meaning, but we will not discuss the meaning of the number today. We'll discuss the meaning of the number in Chapter 10, when we properly study matrices and all their fullness. Okay. Now, maybe you didn't remember how to do that. That's okay. We just kind of retaught it. I don't know why it says we'll learn it in a few minutes. We kind of just saw it. Okay? Now you might say, Mr. Shore, you told us that we were going to create a product, we're going to learn to multiply, to produce a vector answer. And that does not look like a vector, Mr. Shore. That looks like a number. That's the same thing you got when you did a dot product. So I'm not saying that this is how we do vector products, cross products, exterior products. I'm saying that this is a precursor skill to finding vector products. We can't do our new type of multiplication unless you know this skill. But this is not how we actually do our vector multiplication. Not quite. Okay, so this is a prereq skill, background skill. Okay, now we're on the next page. How do we exactly find the product of two vectors? And I don't mean dot product. We have a brand new type of product called the vector product, the cross product, or some people call it the exterior product. Which means they call the dot product the interior product. Okay, so since we're seeking a vector product, our answer has to be a vector with magnitude and direction. And there are a few typos here. The way we set them up is like this. Let's say you had the vector I. I'm sorry, let's not use I, that's a bad choice. How about U? And let's say the vector was, I don't know, negative 10, 24, 0. And let's say that the vector V was the vector negative 3, 2, 6. If you want to find the vector product or the exterior product or the cross product, then the first thing you do is you draw yourself a determinant with the top row ijk. ijk. Now, do you remember I and J? They were famous players in our story. They are main characters, you could say, in the plot. Again? So the ijk that you see there, those stay there always. Like every problem you do, you just put those across the top row. It doesn't matter what vectors U and V are, you always put that, you always set it up the same way. Then in the second row, you put, if you're going to find U cross V, then you would put U in the second row and V in the third row. Very, very important. Do not mix the rows. If you mix the rows, you get the wrong answer. So if it says you're going to find U cross V, then you put U first and then V. Second row is U. Third row is V. Okay, so what's the top row? It's always the same. You're kidding? IJK means I'm just kidding. Oh, you mean that IJK? Yes. I hat, J hat, K hat. Top row, always. Row 2 is your first vector. Row 3 is your second vector. Always. Okay, if you want to do V cross U, then you would actually put the negative 3, 2, 6 in row 2 and the negative 10, 24, 0 on the third row. And you get a different result, by the way. Okay, so anyway, that's how you set them up. Now, the right side of this big formula is really awful. Look at that. I don't think you really want to memorize that. So as long as you stick to that trick where you draw the 6 diagonal lines, you do not need to memorize what I just highlighted. That's good news. You just have to remember how to draw it, and then draw the little 6 lines, and you'll get the same answer that way. Okay, so I will not even use the right side of this formula today at all. Okay, the first one I'm going to do is a very trivial example, like super basic, but it does teach us something interesting. And Mr. Shore meant to delete these 3 lines before handing this out to you. So I would like this to be deleted. Okay, so just scribble it out. Also, there's another typo here. There weren't supposed to be absolute values on here. So that's a more serious typo. There are not supposed to be those double vertical bars. So I had them, these guys, but you need to scribble them out. They do not belong there. We're not finding a magnitude, we're finding a vector. Okay? All right, so how do we do this? Well, we're going to do the same thing we did when we had all numbers. So we're going to go ahead and copy the first and second column outside the matrix. Let me zoom in a little so we can see better. Okay, so we first write I hat 1, 0. That's just copying this first column outside. And then J hat 0, 1. Okay, then we draw our 6 diagonal lines. Green, 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 and blue, blue, blue. Fortunately for us, there's a lot of 0s and 1s. So that means when we follow the green lines, we literally get 0 I hat plus 0 J hat plus 1 K hat. When we follow the blues, we get 0 K hat plus 0 I hat plus 0 J hat. Then we take the results of green and subtract off the result in blue. So basically we're taking 0, 0, 1, and we're subtracting off 0, 0, 0. I'll color code it. We're subtracting off 0, 0, 0. Okay? So what is my answer? 0, 0, 1. Also known as K hat. So this is kind of a dumb problem in a lot of ways. I basically took I hat and I cross-producted it with J hat, and I got K hat. So this is kind of a neat little permanent relationship. What exactly are I, J, and K? They're all 3 unit vectors, okay? They are responsible for the movements in the I direction, also known as the X direction, the Y direction, and the Z direction, respectively. Okay, so not only are they unit vectors, and they all have their own individual directions, they share this relationship. I cross J is always K. All right? Okay, so we'll talk more about that a little bit later. Let's go to a less trivial example, one that actually has more meaningful numbers in it. Oh, actually there's a comment. If I cross J is K, what do you suppose J cross I is? Okay, let's put the cell phones away. What would J cross I be? Do you think it's still K? You know, because 5 times 7 and 7 times 5 is both 35. Or do you think it doesn't really work like that in this world of vectors? I times J is K. Do you think J times I is also K? Turns out it is not. It is negative K. Okay? Okay. It's actually negative K. We won't prove it, but I could redo this exact problem I just did with rows 2 and 3 swapped, and you would see that it actually comes out negative, is what would happen, negative K. In other words, vector multiplication, exterior multiplication, cross multiplication is not commutative. AB is not BA, you know? So we would say, actually the correct thing to say here is no, I cross J is actually the opposite of j cross I. That's the truth. So this means you have to be real careful when you're building your matrix. If somebody says, hey, find U cross B, and you accidentally put B in the second row, you will get the wrong answer. It'll be off by a negative. The whole answer will be the opposite signs. It's not the end of the world. You could fix it, but you probably wouldn't know you made that mistake, right? Okay, so it's not commutative. Let's do a more meaningful example that has real numbers, more interesting numbers in it. Again, you had some extra stuff down here. Just cross it out. I shouldn't even have put anything there. Let's just take the problem, build our own matrix. What goes across the top always? I hat, j hat, k hat. No kidding. And then, what goes in row 2? In this case, vector u. Yes, so 2, 3, negative 5, and then you save the last row for the last vector. Okay, good. Alrighty, let's do our diagonals. So, first we have to copy the inside 2 columns to the right of the bar. So, I hat 2, negative 6, j hat 3, 1, and follow the little green lines. 12i, 30j, 2k. Follow the blue lines. Negative 18k. I'm going to put that under the 2k, obviously. Then we have a negative 5i. I'll put that under the 12i. And there's an 8j. And be careful. Although we combine those by addition, we ultimately end up subtracting on this problem. So you just got to be really, really careful to remember that. So it actually ends up being 17i hat, 17i hat. Oops, my page just scrolled by itself. So it's 17i hat. What do I have for j's here? What is it? It's 22, right? Because it's 30 minus 8. And then it's 2 minus negative 18. So what's my k hats? 20, right. So you can write that back into this form if you like. After all, the question was written like this. So you might as well answer like this. 17, 20, 22, 20 in brackets. So if they give you the problem in brackets, then answer the question in brackets. That's the courtesy. If they give you the question with i's, j's, and k's, then write your answer with i's, j's, and k's. Okay, good. So it turns out that this answer, 17, 22, 20, has physical meaning. Its direction has meaning. Its magnitude has meaning. And its 3 numbers have meaning. But today we don't need to discuss that. We don't really care what this means today. We only care that we were able to learn to find it, because it's a lot of work to find it. And I don't think we should try to bite off more than we can chew. Okay, so today we're just learning to find a cross product vector. Now you try using these ones. And your paper is wrong. Originally when I made this lesson, I had used the vectors that are there on your paper, but I'd like you to update them. Instead of vectors B and C, I'd like you to write the vectors I have here, vectors U and V, because these are the vectors we finally did end up putting into your model. Do these look familiar? Yeah. So update the problem a little bit, sorry about that, and see if you can find the exterior product. Then we're going to build it out of a straw or pipe cleaner and put it in the model so we understand it. Okay? And then that'll be the end of the lesson. So we set it up, IJK, copy the first 2 columns. Okay, draw the lines. We'll do blue and red. So we'll do red first. So negative 3i hat, negative 2.25j hat,
these get added, so you can just preserve their signs. And then the other direction is 4.5 k hat, negative 1.5 I hat, and just 1 j hat. Okay, you guys, so you have your red diagonals, which gives you negative 3 I hat minus 2.25 j hat minus k hat. And then you have your blue diagonals, which gives you 4.5 k hat minus 1.5 I hat plus 1 j hat. And then if you want to, you could just kind of write this as a little vector. Make sure it's in order, I, j, k. And then write the red vector in order, I, j, k. And then subtract the vectors. So you're actually, this is kind of a neat way to show your work. It's super tidy, and it doesn't use much space on the paper. So just be careful. It's negative 1.5 minus negative 3. Yeah, student just caught my error, the red minus the blue. So make sure you always do the down and to the right diagonals minus the up and to the right diagonals. Thank you. I was about to get the wrong answer. By the way, how would my answer have looked? It would have been wrong in what sense? All the signs would be backwards, right? So if I got plus, 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 it actually should have been minus, 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 or something like that. Yeah. Right. Okay. So anyway, thank you for helping me fix that. Negative 3 subtract negative 1.5. So it's negative 3 plus 1.5. Negative 2.25 subtract 1. So that's negative 3.25. And negative 1 minus 4.5, negative 5.5. And this answer came out negative, 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 which is a coincidence. Okay? It's not like all of them are going to come out negative, negative, negative. Okay? All right, so what is this thing? Well, this is the exterior product. This is the cross product. Some people call it the vector product. What is it? Well, we'll talk a lot about what it is in the days to come. But right now, let's just build it. Now, you're going to be thinking like, oh, man, I don't want to make another straw. Okay, don't worry too much about its magnitude. I calculated the magnitude of this vector earlier, and let me see if I still have that on my screen. I think I do here. Yeah, it's going to be right here in a second. I took 2.25, that's basically 1.5, negative 1.5 squared, plus 3.25 squared, plus 5.5 squared, and I got something, 43, and then I squared that. It turns out the magnitude is 6.6, okay? And to me, today, that doesn't really matter too much. The magnitude of U cross V is about 6.6. So I don't want to talk about what the 6.6 means today, and I don't want to talk about that, but I do want to build this thing. So imagine making a straw that is 6 units long. 6.6 units long. That's a pretty big straw, right? Okay. So even by our models, let me see if I can show how long that would be. It's going to be twice the length of your entire box. More than twice the length of your entire box you built. Pretty big.